Hi everyone. Okay, so today we're going to jump into some of the basic rules of probability. Last time, what we did was we went over a bunch of different rules. We went over the arguments from authority, but we also went over some of the basic notation for probability. And today, I'm going to largely assume that you know how to understand that notation, that you know the interpretation of it. And we're going to jump in and we're going to go into a few of the rules for probability. So in beginning with the rules for probability, what we're going to do is begin with some basic assumptions about how probability generally works. And some of these things, if you had a basic statistics course, will seem pretty familiar, and so it shouldn't be that strange to you. Remember that when it comes to what it is that we're talking about the probability of, I'm going to trade a bit between events and statements. By the time we get to what's called Bayes' theorem, I'm just going to do everything in terms of statements. But for now, these basic rules of probability are easier to understand in some cases if we use event language. So I'm going to stick with this event language a little bit. So the thing that we're going to be largely, the basic idea is that probabilities of events or statements are going to fall generally between 0 and 1. And so we're not going to be dealing in statements or events that have probabilities of 1 or 0. We're going to be dealing with statements that have a probability somewhere between 1 and 0. Right? But still, it's important to know that events or statements can have probabilities of 1 or 0, and it's important to know exactly what that means in the context of our rules for probability. So in this case, what we have, if an event has the probability of 0, then that's because the statement is a contradiction. And the basic idea is that a contradiction is a statement that must be false and or an event that can't happen. So to say that an event has a probability of 0 is to simply say that it's an event that cannot occur. So here's a way you might put it. Richard traveling to Paris, France, while at the same time traveling to Potsdam, New York. Those things are in some sense contradictions. So imagine that I get on a plane to Paris, France, and I say, well, I'm going to Potsdam, New York. That's an event that can't happen as long as it's assumed that I'm going to Paris, France, because Paris, France, and Potsdam, New York are two different locations. To put it in terms of statements, you might ask what's the probability of me being both in Potsdam, New York, and in Paris, France? And the natural answer there is to say that the probability is 0 because those are geographically distinct locations, and human beings, as far as we know, can't occupy two positions in time at the same time. So, so this is the basic idea. And so the next one is that a probability of an event equaling 1 means that it's a tautology. So tautologies are statements that must be true. And so these kinds of statements that must be true are usually statements that sound kind of trivial. They're things like the probability of, say, Richard being in Potsdam, New York, or being anywhere else, right? So there are two options: either I'm here or I'm somewhere else. There's no in between. Either I'm here or somewhere else, and so since that's obviously true, we would assign it a probability 1. In terms of events, this would be the probability of an event that must happen. And so the idea here is that if an event must happen, then it equals 1. Right. So we're going to be assuming all of this in the background. We're not going to be dealing in probabilities of 0 or probabilities of 1 for events. We're going to be dealing with probabilities. We're going to be dealing with values that are somewhere in between. So these events are in question are not things that must be true or things that must be false. These are going to be events that could be true or could be false, and they could be true or could be false with different probabilities. Okay, so back to the rules of the calculus. What I'm going to do with you all today is I'm going to cover the conjunction rules and then go over a few of the conjunction exercises and the negation rule. Next time, we'll go over the disjunction rule. I'll give you the definition of conditional probability and then transition into what's called Bayes' theorem. All of this is to provide you with a basis for moving forward into looking at how this thing that I'm calling Bayes' theorem serves as a model for how inductive reasoning might work. And so we're going to start off with these really basic exercises so you get a sense of how these different rules work, and then we're going to build up the Bayes' theorem. Okay, so the conjunction rules. There are 2 conjunction rules. There are going to be 2 disjunction rules as well, but we're going to focus on 2 conjunction rules for today. And the 2 conjunction rules say this. They're the restricted and general conjunction rules, and the restricted conjunction rule says that if you want to calculate the probability of a conjunction, then you need to multiply the probability of one conjunct with the probability of the other. So in this case, we have the probability of A and B. Well, to calculate the probability of A and B, we multiply the probability of A by the probability of B. Now, this assumes that the events in question are independent. That is, it assumes that the events in question do not influence one another. And so the idea here is that whatever happens in the first case, the second case is not influenced by it. And so, for example, we would apply this if we wanted to know like the result of getting heads and then tails in 2 flips of a coin. When we flip the first coin and get heads, that will have no bearing on whether the second coin will get head. The second coin will come up heads, right, or tails. That those events are independent of each other. So just because you get heads the first time, that doesn't mean that you're going to get heads the second time. In fact, you know, there's this kind of disposition we have, which is like, oh, I've been, you know, if you're gambling or doing anything that kind of has the risky character of gambling to it. If you've been on a losing streak, you think to yourself, oh, I'm going to win. But if the events in question related to what you're gambling on are all independent of each other, then you're actually engaged in a kind of fallacy. Sometimes it's called the hot hand fallacy. Sometimes it's called the gambler's fallacy. You're treating independent events as if they're dependent on each other. And so the idea here is that we should only apply the dependence rules, or we should only apply the restricted conjunction rule when the events in question are independent. Now, where the events are dependent on each other, we should apply the general conjunction rule. So the probability of a conjunction A and B is equal in this case to the probability of A multiplied by the probability of B if A. Right? So this is the way you want to understand this. What we're doing is we're saying that the probability of the conjunction is equal to the probability of the first event happening multiplied by the probability of the second event happening if the first one has already happened. Hopefully this will become clear when we look at a couple of the exercises I have for you, but the basic idea is this. We want to capture dependence by representing somewhere in the equation on the right-hand side in this case, how one event is influenced by the other, or that one event is influencing the other. How its influence will depend on the specific problem. But the general conjunction rule then will give us different results if the events in question are dependent on each other. If we applied the restricted conjunction rule to a problem where the events are dependent on each other, then we would get the wrong results. In this case, if we apply in this case, we need the general conjunction rule to get the right result. Okay, so just to review, dependence, realize the idea here, and you'll see this as it gets characterized in different problems, is sort of the way in which these events may or may not influence each other. So 2 events are independent if there's no influence of one on the other. So this would be the case, sorry about that. This would be the case where we have a coin, and the coin, we want to ask, well, how does the I guess result of one toss of the coin influence later tosses? Well, they don't, right? They're probabilistically independent events. In the case of dependence, this might be more like you have a standard 52 card deck, and you have 4 suits, hearts, diamonds, clubs, spades, and you want to know, well, what's the probability of drawing drawing a heart and then drawing another heart? Well, if you don't put that first heart back in, then the probability is going to be the probability of getting a heart in a later draw is going to be influenced by that first draw. Okay, so this is basically the way you want to think about it. In the kinds of problems I'll provide you, what we'll see are situations where I'll specify, hey, we put something back in, hey, we didn't put something back in, and you need to be able to see whether that demands that you use the general or restricted conjunction rules. Okay, so let's look at a couple of exercises just to give you a feel for how this might work. And The basic idea here is that we get a sense of how you would apply these rules so that you can use them for exercises. So let's look at the first one on the left-hand column. You rolled a 3. What is the probability that the next roll will be a 4? So strictly speaking, this is a little under-described, so I'm sorry about that, but this problem asks, what I want this problem to ask is, what's the probability of rolling a 3 and then a 4 in a 6-sided fair die, right? So one of those little white die with the black dots that you might be familiar with. So in that kind of die, the basic way in which this would work is that you would have to say that as long as it's a fair die and there are only 6 possible outcomes, then every outcome will be equally likely. So the probability of rolling a 3 is 1/6. Now we want to know the probability of rolling 1 3 and then 1 4. Well, in this case, we would have to say that we would apply the restricted conjunction rule. And that's because the rolling of the different numbers on the different sides of the die are independent. They don't influence each other. And so in this case, what you would do is you would take the probability of getting a 3, 1/6, and multiply it by the probability of getting a 4, 1/6. And so that would equal 1/36, right? So in this case, then, we would apply the restricted conjunction rule and we would get the result of 1/36. Let's look at a slightly different case. This one's a little more ambiguous. So on the right-hand side, the first problem, what is the probability that your next 2 cards from the deck will be face cards? So we have to think about the composition of the deck here, and I'll just give you some answer. I'll give you some answers since you may not know a lot about decks of cards. The probability that, you have 4 suits, and for each of the 4 suits, you have 3 face cards, jacks, kings, queens, right? So in this case then, since we have 4 suits and we have 3 face cards each, we would have 12 face cards total in the deck, right? So from here, we ask ourselves, well, what's the probability that in 2 draws, I get face cards, or that I get a face card and then a face card? This depends on an important feature of the situation, which is where I draw a card and then I don't put the card back, or I draw a card and do put it back. And which of these happens, or which of these is a part of the description of the problem, will influence which rule is applicable to the problem. So let's think about it this way. Imagine that I draw a face card, I draw a card from the deck, and then I throw it away, right? Well, the next draw is going to be influenced by that second one, right? And I'll explain just how in a moment. But then that suggests that we should use the general conjunction rules, because the general conjunction rule, because the events in question are dependent on each other. So there are 52 cards in a standard deck. There are 12 face cards. And in the first draw, then, we have a probability of 12/52 of drawing a given face card. Now let's assume that that first event happened. We throw out the card and don't replace it. Now we have 51 cards, and because we've drawn a face card, we have 11 face cards left. So the probability of drawing a face card with the second draw would be 11/51, right? From there, you would multiply those values together, and then you would get the result. So notice that in this case, we have to apply the general conjunction rule, because by changing the probability to 11/51 from 12/52, what we're assuming is that the first draw resulted in a reduction in the number of cards and the number of face cards in the deck, right? So we would then multiply the values and get the corresponding result. Okay, so those are 2 exercises. They should give you a feel for how this works, but for now, let's go over to another rule. And that rule is the negation rule. So remember that tilde, that little squiggly line next to the A on the right-hand side of the equation, just below the negation rule, it means not. So this just says the probability of an event happening or a statement being true is equal to the probability of it's not being true or it's not happening. So this assumes in the background that either something will happen or it won't happen, right? And so the probability that something will happen or that won't happen is equal to 1. And so the probability of something happening must be equal to the probability of 1 minus the probability of that thing not happening. And so the negation rule provides us with some resources for being able to address certain kinds of problems, namely the problem of trying to figure out things like in 3 tosses of a coin, what is the probability of rolling at least, or of flipping at least 1 tails, of getting at least 1 tails. Sorry about that, I'll fix that later. So the at least 1 tails, what we would have to do is first answer the question of what is the probability of getting no tails at all, right? So imagine we flip a coin 3 times and we want to know the probability of getting no tails at all. So in this case, then we know the probability of getting heads or tails in this case, no matter which way you go, is 0.5. So the probability of getting 3 heads using the conjunction rule would be the probability of 0.5 times 0.5 times 0.5, right? So we just multiply those 3 together. It's equal to 0.125. So in this case, then we take the probability of at least 1 tails in 3 tosses, which would, and then we subtract from, what that's equal to is 1 minus 0.125. So notice that the probability of getting no tails is the negation of the probability of getting at least 1 tails, right? So if it's not the case that I got no tails, then I must have gotten at least 1 tails. So this is the application of the negation rule to this problem. And so in this case, then, the probability of at least 1 tails in 3 tosses is 1 minus 0.125, which equals 0.875, right? So notice what happens here is that if we were to keep on attaching new heads to the conjunction in the first part of the problem, then we would get a smaller and smaller number. And the probability of getting at least 1 tails in whatever number of tosses we're doing would become correspondingly bigger. This is to say that the probability of just a straight head sequence in a fair coin, in a toss of a fair, several tosses of a fair coin, that sequence of just getting a bunch of heads is actually a pretty improbable sequence, even though the events don't influence each other. So, so there you are. Okay, so these are the disjunction rules. We're not going to get to them for now, but take a look at the exercises, get a sense of how this conjunction stuff works, and then we'll turn to these disjunction rules next time. We're hitting up onto quiz 8 now, so that means we're on the last 3 quizzes. So this week and then the next 2 weeks we'll have quizzes 8, 9, and 10. And you'll have until the end of finals week to complete all of those quizzes. So make sure that if you're behind, that you're going, I think it's probably advisable that you go ahead and start now and start getting quiz 5 and 6 and 7 done. It'll make your life a lot easier, especially as we start getting into some of this more mathy stuff with the different probability rules. Anyways, I'll see you next time.